Snowflake is one of the most widely adopted cloud data platforms in the world. But in our experience, most teams using it don't fully understand the architecture underneath. And that's where a lot of performance and cost problems come from. So in this video, we are going to explain how Snowflake's architecture actually works, layer by layer, and then walk through the most common places where teams misuse it. Traditional databases bundle three things together: storage, compute, and services. They're all in one system. If you need more compute, you scale the whole thing, storage included. If you need more storage, you're paying for compute whether you need it or not. Snowflake's fundamental design choice was to separate these into three fully independent layers. Each one scales on its own without affecting the others. Let's look at what each layer actually does. Snowflake stores all data on Cloud Object Storage, S3 on AWS, Blob Storage on Azure, Google Cloud Storage on GCP. You never interact with the storage layer directly. You don't manage files, don't choose storage locations, don't worry about disk space. Snowflake handles everything. You're built on compressed data volume, and it's relatively inexpensive. But Snowflake doesn't store data as raw files. It automatically organizes everything into micro-partitions, compressed columnar chunks, each between 50 and 500 megabytes. Each column within a partition is compressed using the most efficient algorithm for its data type. And here's the important part. Snowflake stores metadata for every partition, specifically the min and max values for every column. So when you run a query with a where clause, Snowflake checks the metadata, identifies which partitions could possibly contain matching data, and skips everything else. This is called partition pruning. It's Snowflake's version of indexing, except you never have to create or maintain anything. It happens automatically. The compute layer is where queries actually run, and it's the most architecturally significant part of Snowflake. A virtual warehouse is an independent cluster of compute nodes. The critical concept: warehouses are completely independent of each other. You can run 5, 10, 20 warehouses simultaneously, all reading the same data from storage, and they don't interfere with each other at all. Warehouses come in t-shirt sizes, XS through 6XL. Each size doubles the nodes and the cost. But here's the nuance most people miss. Because compute doubles, the same query runs in half the time for the same total cost. So warehouse sizing isn't really about cost. It's about throughput and concurrency. Warehouses can also auto-scale horizontally. If 20 analysts hit the same warehouse and queries start queuing, Snowflake automatically spins up additional clusters to handle the concurrency, then scales them back down when demand drops. This is scaling out, not sizing up. And warehouses auto-suspend when idle and auto-resume when a query arrives. You only pay when compute is actually running. This is fundamental to how Snowflake's cost model works. The cloud services layer handles everything that isn't storage or query execution: authentication, access control, query optimization, metadata management, and transaction control. When you submit a query, it hits this layer first. The optimizer parses the SQL, determines the most efficient execution plan, checks which micro-partitions to read, and hands the plan to the warehouse. It also manages result caching. If the exact same query runs again and the underlying data hasn't changed, Snowflake returns cached results in milliseconds. No warehouse compute used, completely free. This layer is always running, managed by Snowflake, and rarely built separately. When these three layers work together, you get capabilities that don't exist in traditional databases. Zero copy cloning. Create an exact copy of an entire database in seconds with zero additional storage, because the clone just points to the same micro-partitions. Time travel. Every change creates new partitions while old ones are retained, so you can query data as it existed at any point in the past, up to 90 days. Secure data sharing. share live data with other Snowflake accounts without copying or moving anything. These aren't add-on features, they're natural consequences of how the architecture is designed. So that's how the architecture works. Now, understanding it makes certain common mistakes much easier to spot. Here are the 4 we see most often. The most common mistake: running all workloads through 1 or 2 warehouses, ETL jobs, analyst dashboards, ad hoc queries, data science, all competing for the same compute. When the ETL runs, dashboards slow down. When a data scientist fires a heavy query, analysts queue up. The whole point of Snowflake's separated compute is that you can create purpose-built warehouses for each workload, a dedicated XS for BI dashboards, a medium for nightly ETL, a large for data science. They all read the same data, they never interfere, and with auto-suspend you only pay when each one is running. The total cost is often the same or lower, but performance is dramatically better. A query is slow, so someone bumps the warehouse from medium to XL. The query runs faster, but compute costs are now 4 times higher per hour. The actual problem is usually visible in Snowflake's query profile: a full table scan because the filters aren't selective enough, a select star pulling every column when only 3 are needed, or a join pattern forcing massive data shuffles. Bigger compute doesn't fix bad SQL, it just makes it more expensive. The right approach is always look at the query profile first, fix the query, and only then consider whether the warehouse needs resizing. Snowflake doesn't use traditional indexes. Micro-partitions and partition pruning handle most of it automatically. But for very large tables, over a terabyte, roughly 1,000 plus micro-partitions, data can become scattered to the point where pruning isn't efficient anymore. That's when clustering keys help. They tell Snowflake how to reorganize partitions so related data is co-located. But clustering has a cost. The automatic reclustering service runs in the background and consumes compute, so it only makes sense on large tables with selective queries. Cluster on your most common where clause columns, typically dates or low cardinality categories. Don't cluster on UUIDs or high cardinality columns. Don't use more than 3 or 4 columns, and revisit your choices every 6 to 12 months as query patterns evolve. Snowflake's default auto-suspend is 10 minutes. Most teams leave this unchanged across every warehouse, but different workloads have different patterns. A BI warehouse getting burst queries every half hour doesn't need to stay warm for 10 minutes between bursts. Set it to 1 minute. An ETL warehouse running continuous batches might need a longer suspend time to avoid cold start overhead on each load. There's no single right answer. The point is to match the suspend time to how each warehouse is actually used. Using the same default everywhere is almost always leaving money on the table. Snowflake's architecture is genuinely elegant. 3 independent layers, each doing one job well. Most performance and cost problems we see come from teams using Snowflake the same way they used their previous database, without designing around how these layers actually work. If you're running Snowflake, try auditing your setup against these 4 patterns: workload isolation, query optimization before upsizing, clustering key discipline, and auto-suspend tuning. That's usually where the biggest gains are. We share technical deep dives on data platforms, architecture patterns, and the things we see across the industry. Follow along if this was useful. There's a lot more coming.